Picture this. You're standing in your backyard on a clear night, looking up at the stars. You can see Mars glowing red in the distance, maybe catch a glimpse of Jupiter if you're lucky. But there's something out there, something massive, that you'll never see with the naked eye. Something that might be larger than Earth itself, silently orchestrating the dance of worlds at the very edge of our solar system. For over a century, we thought we knew our cosmic neighborhood pretty well. 8 planets, some moons, a few asteroid belts, and the scattered debris of the Kuiper Belt stretching out beyond Neptune. Case closed, right? Well, not quite. In the past decade, astronomers have been discovering something deeply unsettling. Objects in the far reaches of our solar system, they're not behaving the way they should. Their orbits are clustering in patterns that defy explanation. It's as if some invisible hand is shepherding them, guiding them into arrangements that should be impossible in an empty region of space. The first hint came from an object called Sedna, discovered in 2003. This dwarf planet follows one of the most bizarre orbits we've ever seen. At its closest approach, it's still 3 times farther from the Sun than Neptune. At its farthest point, it ventures out to nearly 1,000 times Earth's distance from the Sun. That's a journey that takes over 11,000 years to complete, but Sedna wasn't alone. As more powerful telescopes came online, astronomers began finding similar objects, each one following these incredibly elongated, tilted orbits that seemed to point in roughly the same direction. The odds of this happening by chance? About 1 in 14,000. Then there's what researchers call the Kuiper Belt cliff. If you plot the number of objects we find at different distances from the Sun, everything looks normal until you reach about 50 astronomical units. That's 50 times Earth's distance from the Sun. Then suddenly the population just drops off. It's like hitting a wall. Here's where it gets really interesting. We've become incredibly good at finding planets around other stars. We've discovered thousands of them, some orbiting stars hundreds of light years away. Yet here in our own solar system, there might be a world 5 to 10 times more massive than Earth, and we've somehow missed it. The scientists leading this cosmic detective story are Mike Brown and Konstantin Batygin from Caltech. Their computer simulations tell a fascinating story. When they model the outer solar system with these strange objects and their peculiar orbits, everything makes sense. If there's a massive world out there unseen, pulling strings like a cosmic puppet master, this hypothetical planet would need to be at least 5 times more massive than Earth, orbiting somewhere between 400 and 800 times farther from the Sun than we are. Think about that distance for a moment. Light from the Sun, which reaches Earth in just over 8 minutes, would take hours to reach this distant world. The gravitational fingerprints are everywhere once you know how to look. The clustering of distant objects, the tilted orbits, even the slight tilt of our Sun relative to the planets, all of it could be explained by this invisible giant. It's like finding footprints in fresh snow when you thought you were alone in the forest. If there's truly a world out there larger than Earth, silently shepherding our solar system from the shadows. A planet that has witnessed the entire history of our solar system from the ultimate vantage point. The edge of forever. The year was 2016, and the astronomy world was buzzing with excitement over a paper that would shake the foundations of planetary science. Mike Brown and Konstantin Batygin had just published research that didn't just suggest Planet 9 existed. It practically demanded it. Mathematics has a funny way of revealing truths that our eyes can't see. Just as Einstein's equations predicted black holes decades before we found them, Brown and Batygin's calculations pointed to something extraordinary lurking in our outer solar system. By 2016, astronomers had cataloged 6 objects in the distant Kuiper Belt with truly bizarre characteristics. Worlds like Sedna, 2012 VP 113, and others with names that sound more like passwords than planets. Each of these objects follows an extremely elongated orbit that takes thousands of years to complete. Here's what made astronomers sit up and take notice. All 6 of these objects have their closest approach to the Sun pointing in roughly the same direction. The probability of this happening by pure chance was less than 1 in 14,000. To put that in perspective, you're more likely to be struck by lightning twice in your lifetime, but it gets better. These objects weren't just clustered in where they approached the Sun. Their orbital planes were tilted in similar ways too. It's as if some massive gravitational influence was herding these distant worlds into similar orbital families. When Brown and Batygin fed this data into their computer simulations, the answer that emerged was both elegant and mind-bending. There had to be a 9th planet out there, and its properties were surprisingly specific. The math demanded a world between 5 and 10 times more massive than Earth, orbiting at a distance of 400 to 800 astronomical units from the Sun, taking anywhere from 10,000 to 20,000 years to complete. A single orbit. Think about that orbital period. When this world was last at its closest approach to the Sun, human civilization was just beginning to develop agriculture. The next time it reaches that same point, we might be exploring the galaxy. The simulations revealed something even more fascinating. Planet 9 doesn't just explain the clustering of these distant objects. It explains a whole host of solar system mysteries. Our Sun has a slight tilt relative to the orbital plane of the planets, about 6 degrees. Planet 9's gravitational torque could create exactly this tilt over billions of years. Then there are the detached objects, worlds that orbit so far from the Sun that Neptune's gravity shouldn't be able to touch them. Planet 9 provides the answer. During the early chaotic period of our solar system's formation, Planet 9 would have gravitationally scattered these objects outward. The computer simulations are mesmerizing to watch. You can see our solar system evolving over millions of years, with Planet 9 acting like a shepherd dog, keeping the flock of distant objects organized through pure gravitational influence. Without Planet 9 in the simulation, these objects scatter randomly. With it, they cluster exactly as we observe them today. The mathematics also reveals why Planet 9 has remained hidden for so long. At its predicted distance, it would reflect virtually no sunlight. We're talking about an object that would be 600 times fainter than Pluto, which was already barely visible when we discovered it in 1930. Yet the gravitational evidence is overwhelming. It's like detecting a person walking through fresh snow by their footprints, even when you can't see the person themselves. Planet 9 has left gravitational footprints throughout the outer solar system, and once you learn to read them, the story they tell is unmistakable. The math is compelling. But all of this raises the ultimate question: if Planet 9 is mathematically inevitable, where exactly is this phantom world hiding? The history of astronomy is filled with phantom worlds, mathematical predictions, and thrilling moments when invisible planets finally reveal themselves to human eyes. Let's travel back to 1846. Uranus had been discovered in 1781, but there was a problem. It wasn't behaving properly. Its orbit was slightly off, as if something was tugging at it gravitationally. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated where an unknown planet would need to be located to cause Uranus's orbital irregularities. Then, in September 1846, German astronomer Johann Galle pointed his telescope to the predicted location and found Neptune, an entire world discovered through mathematics before it was ever seen. The success was so remarkable that astronomers immediately began looking for more hidden worlds. Le Verrier became convinced there was another planet inside Mercury's orbit, causing similar perturbations. He even named it Vulcan. For decades, astronomers reported sightings of this elusive inner planet, but Vulcan was a phantom. What astronomers had attributed to a hidden planet was actually Einstein's relativity in action. Sometimes the mathematics points to new physics rather than new worlds. Then came Pluto's story. Percival Lowell had calculated that another planet beyond Neptune was perturbing the outer planet's orbits. In 1930, young Clyde Tombaugh spotted a tiny moving dot. Pluto seemed to vindicate Lowell's predictions, except it didn't. When we finally measured Pluto's mass, we discovered it was far too small to cause the orbital perturbations Lowell had detected. The irony deepened in 2006 when Mike Brown, yes, the same Mike Brown now hunting Planet 9, helped reclassify Pluto as a dwarf planet. These historical searches taught astronomers valuable lessons. The Neptune discovery showed that mathematical prediction could reveal hidden worlds. The Vulcan search demonstrated that unusual observations might point to new physics. And Pluto's story reminded everyone that the cosmos loves to surprise us. Unlike previous phantom planet hunts, the Planet 9 hypothesis is built on multiple independent lines of evidence. It's not based on tiny orbital perturbations that could be measurement errors. Instead, it explains large-scale patterns in the outer solar system that have emerged from decades of improved observations. The technology driving today's search would seem magical to those 19th century astronomers. The Subaru telescope in Hawaii can photograph areas of sky in a single night that would have taken Clyde Tombaugh months to cover. The dark energy camera can detect objects millions of times fainter than anything visible to the naked eye. Then there's the upcoming Vera Rubin Observatory. Starting soon, this revolutionary instrument will photograph the entire visible sky every few nights, creating a time-lapse movie of the cosmos. If Planet 9 is out there, Rubin will likely find it within a decade. But why is Planet 9 so much harder to find than Neptune was? At Planet 9's predicted distance, it would receive 180,000 times less sunlight than Earth does, and reflect 180,000 times less light back to us. Planet 9's predicted location also spans an enormous area of the sky, roughly 2,000 times larger than the full moon. Modern searches face new challenges too. Light pollution now washes out much of the night sky, and the sheer volume of astronomical data has become overwhelming. Some surveys generate more information in a single night than astronomers used to collect in entire careers. That's where citizen science comes in. Projects like Backyard Worlds, Planet 9 allow anyone with an internet connection to help search through telescope data, looking for the telltale signs of moving objects. There are alternative theories to consider. Some astronomers suggest the clustering might be caused by a primordial black hole or modifications to gravity itself at these extreme distances. The history of phantom planets reminds us to keep an open mind, but here's what history tells us most clearly. When multiple lines of evidence point to a hidden world, and when the mathematics is compelling, we usually find something remarkable. History shows us that when the math predicts a planet, we usually find it. If Planet 9 exists, it doesn't just add another world to our cosmic family tree. It fundamentally rewrites the story of how our solar system formed and evolved. Planet 9 would be what astronomers call a super-Earth, a planet larger than Earth but smaller than Neptune. Super-Earths are incredibly common throughout the galaxy. They're the most frequently found type of planet around other stars. Nearly every planetary system we've discovered has at least one super-Earth dot except ours. Our solar system has been the weird one, the oddball with no super-Earth anywhere to be found. We jump straight from rocky planets like Earth and Mars to gas giants like Jupiter and Saturn, with nothing in between. Planet 9 would solve that mystery dramatically. We do have a super-Earth. It's just been hiding in the outer darkness for billions of years. But how did it get out there? Computer simulations of the early solar system paint a picture of absolute chaos. Planets forming, migrating, colliding, and sometimes being ejected entirely from their birth systems. There's a hypothesis called the Grand Tack that describes how Jupiter initially formed much closer to the Sun, then migrated inward before reversing course and moving back outward. This gravitational bulldozer would have scattered smaller worlds in every direction. Planet 9 might be a survivor of this cosmic catastrophe. A super-Earth that was born in the inner solar system alongside the other terrestrial planets, only to be gravitationally ejected to the outer darkness by Jupiter's wandering. That there's an even more exotic possibility. Planet 9 might not be from our solar system at all. During the early days of the galaxy, stars were much more tightly packed together. Stellar encounters would have been common, and planets could have been stolen from one star system and captured by another. 9 might be an alien world in the most literal sense. A planet that formed around a different star in a different part of the galaxy before being gravitationally captured by our sun billions of years ago. If Planet 9 exists, it suggests that super-Earths are not only common in other planetary systems, they might be common in the outer regions of those systems too. We might have been looking for these worlds in the wrong places. Think of Planet 9 as a cosmic sculptor, slowly carving the outer solar system into its current form through gentle but persistent gravitational nudges. Every time it completes one of its 10,000-year orbits, it slightly adjusts the paths of countless smaller objects, gradually organizing them into the patterns we observe today. The gravitational dynamics are truly beautiful in computer simulations. Planet 9 doesn't just randomly scatter objects. It creates what astronomers call resonant chains. Objects get locked into precise mathematical relationships with Planet 9's orbit. Planet 9 would also help explain the absence of super-Earths in our inner solar system. The same gravitational interactions that ejected Planet 9 outward would have prevented other super-Earths from forming or surviving in the inner regions. This has profound implications for the search for life in the universe. Many astrobiologists have focused on super-Earths as prime candidates for hosting life, assuming they would orbit in the warm, habitable zones around their stars. But if super-Earths are commonly ejected to the cold outer regions, we might need to rethink where to search for life. Planet 9 might be our solar system's most alien world, a refugee from cosmic chaos carrying within its icy depths the secrets of our system's violent past and the architectural principles that govern planetary systems throughout the galaxy. The search for Planet 9 has evolved into one of the most sophisticated treasure hunts in astronomy's history. Today's planet hunters wield an arsenal of cutting-edge technology that would seem like science fiction to earlier generations. At the forefront is the Vera Rubin Observatory in the Chilean Andes. When fully operational, this revolutionary telescope will photograph the entire visible sky every few nights, creating a time-lapse movie of the universe. Its massive 3.2 gigapixel camera will be sensitive enough to detect objects nearly as faint as Planet 9 is predicted to be. The Subaru telescope in Hawaii has been systematically searching the northern sky for years, using sophisticated image processing techniques to identify moving objects. Each night, Subaru can cover an area equivalent to 40 full moons, photographing the same regions repeatedly to catch anything that shifts position. What makes these modern searches so powerful isn't just the hardware, it's the software. Artificial intelligence and machine learning algorithms now sift through thousands of images automatically, flagging potential candidates for human review. These AI systems have been trained to recognize the subtle signatures of distant solar system objects. The data processing challenges are staggering. A single night of observations can generate terabytes of information. Advanced computer clusters work around the clock to process this flood of data, comparing images taken on different nights to identify objects that have shifted position. Citizen science has joined the hunt too. The Backyard Worlds Planet 9 project allows anyone with an internet connection to help search through telescope data. Volunteers examine animated sequences of images, looking for objects that move in ways consistent with distant planets. The search strategies have become incredibly sophisticated. Rather than simply looking for any moving object, astronomers now search for motion that matches Planet 9's predicted orbital characteristics. They know roughly how fast it should be moving across the sky and what direction it might be traveling. There are also unconventional search methods being explored. Some astronomers are looking for Planet 9's thermal emission rather than its reflected sunlight. Even at its frigid distance, Planet 9 would still radiate heat from its formation billions of years ago. Recent developments have been particularly exciting. Advanced computer simulations have refined the predictions for Planet 9's most likely location, focusing the search on specific regions of sky. Some models suggest Planet 9 might currently be near its farthest point from the Sun, making it extremely faint, but also relatively stationary. The search faces significant challenges. Planet 9's predicted location covers an enormous area, roughly 2,000 times larger than the full moon appears in the sky. Weather, moonlight, and instrumental problems can interrupt observations for weeks at a time. International collaboration has become crucial. Telescopes in both hemispheres are needed to cover the entire sky, and sharing data between different surveys helps confirm potential discoveries. The search has become a global endeavor. As the search intensifies, so does the excitement in the astronomical community. Every new survey image, every refined orbital calculation brings us closer to answering one of the most fundamental questions about our cosmic home. We're closer than ever to answering that question. The technology exists, the search strategies are sophisticated, and the dedication is unwavering. Planet 9 might be discovered any day now. The hunt for this elusive world represents astronomy at its most thrilling. Close your eyes and imagine standing on the surface of Planet 9. The landscape around you is unlike anything. In the inner solar system, a world frozen in perpetual twilight, where the sun appears as nothing more than a bright star in an alien sky. The temperature hovers near absolute zero, cold enough to freeze air into solid crystals. This is what awaits us if Planet 9 is real. A world that represents the ultimate frontier of planetary exploration. A place so distant and alien that it would challenge every aspect of our space technology. The moment Planet 9 is confirmed, it will trigger a revolution in planetary science that ripples through every astronomy textbook. We'll suddenly have a ninth planet again, but this time it will be a world that truly deserves the title. Discovery would vindicate mathematical prediction in the most dramatic way possible. Just as Neptune's discovery in 1846 proved that celestial mechanics could reveal hidden worlds, Planet 9 would demonstrate that 21st century computational astronomy can uncover Secrets hiding in the vast darkness of space. Planet 9 would immediately become the most important laboratory for understanding super-Earth formation and evolution. Remember, super-Earths are the most common type of planet in the galaxy, yet we've never had one in our own solar system to study up close. What would this world actually look like? Computer models paint a fascinating picture. Planet 9 would likely have retained a substantial atmosphere from its formation, composed of hydrogen and helium, similar to Neptune's. The surface would be a museum of solar system history, preserving a record of conditions from billions of years ago. But discovering Planet 9 is just the beginning. A mission to Planet 9 would represent the ultimate challenge in deep space exploration. Even traveling at incredible speeds, such a journey would take decades to reach its target. We're talking about a mission that would span entire human generations. The technological challenges would drive innovation in ways we can barely imagine. Nuclear-powered spacecraft, advanced ion propulsion, perhaps even solar sails that could harness starlight's pressure to reach unprecedented speeds. A Planet 9 mission would push the boundaries of what's possible. The discovery would also transform our understanding of planetary system formation throughout the galaxy. If super-Earths commonly get ejected to outer regions during chaotic early formation phases, then we've been looking for potentially habitable worlds in the wrong places. This raises fascinating questions about the search for life. While Planet 9 itself would be far too cold to host life as we know it, its discovery would suggest that other planetary systems might harbor frozen super-Earths in their outer regions. Some of these worlds might have subsurface oceans, kept liquid by radioactive heating. The philosophical implications are equally profound. Planet 9 would add another chapter to our story of cosmic humility. It would remind us that even in our own solar system, there are still massive worlds we've never seen. It would suggest that the outer regions of planetary systems might be far more populated and interesting than we've imagined. But what if Planet 9 isn't found? That outcome would be almost as scientifically interesting as discovery. It would mean the orbital clustering has some other explanation, perhaps modifications to gravity at extreme distances, or some other exotic phenomenon we haven't yet imagined. There's also the tantalizing possibility that Planet 9 is just the beginning. If there's one massive world hiding in the outer solar system, might there be others? The search techniques being developed are already revolutionizing our ability to find small, distant objects throughout the solar system. As we stand on the threshold of potential discovery, Planet 9 represents something profound about human nature, our irrepressible drive to explore, to question, to seek out the unknown, even when it hides in the darkest corners of space. Planet 9 might be out there right now, silently orbiting in the cosmic darkness, waiting for that moment when human technology finally becomes sophisticated enough to reveal its presence. It might be a world that has witnessed the entire history of our solar system from the edge of forever, or it might remain forever hidden, a phantom that exists only in our mathematics and imagination. But either way, Planet 9 has already transformed our understanding of what's possible and reminded us that the universe still holds secrets waiting to be discovered. The search continues. The mystery endures. And somewhere in the darkness beyond Neptune, the answer waits. Planet 9 represents not just a new world, but a new chapter in understanding our place in the cosmos. A reminder that even in our own cosmic neighborhood, there are still frontiers waiting to be explored and wonders waiting to be discovered.